Okay, so in this video we're going to go over two different types of equations. One is sketching polar regions from a given set, and the other is writing a set builder notation, right, from a given polar graph. All right, so let's start with sketching the region. Right, so for these next two examples, we'll be asked to sketch the region in the xy plane described by the set. All right, so for our first problem, number one, we are given a set in set builder notation. And again, set builder notation looks like this, right? It is described by, has curly brackets. Right, so the way you read that is this is a set, right? The curly brackets tell me it's a set. What's in this set is an ordered pair, right? And it's a polar ordered pair, right? Where r theta, right? And it describes, well, what must r be? R must be between 0 and 3, and theta must run between 0 and 2 pi. Okay, so this kind of straight bar here, a way to read this is we're looking for points, polar points r theta such that, let's say read that bar, r is between 3 and 0, and theta is between 2 pi and 0. All right, so let's draw our coordinate axes. All right, so our coordinate axis will look nice. All right. Now, in terms of the r runs between 0 and 3. So let's say 1, 2, 3. All right, so they're inequalities. So it's all the values from here, right? Starting at 0 all the way to 3. Right, so all of these values between 0 and 3 are included in our set, right? Or at least the pairs that correspond to that, right? The ordered pairs, right? Along with 0 to 2 pi, right? So not just these, but also the points that correspond with the values out here. All right, so essentially, let me draw. 2 pi is 1/4 revolution. So what we have here is something that looks like this. All right, so it includes all these points, right, from 0 to 3. All these correspond to values between 0 and 3. Again, right, these polar graphs, when r is just a constant, refers to a circle. All right, so we're looking for all of these points, right, from the angles 0 to 2 pi, including the boundary, right, since it's less than or equal to 3. If it was just strictly less than 3, we would use the dotted line for that boundary values. But this is every single point in this region. All right, so these two, the set builder notation corresponds to this sketch right here. Right, a circle of radius 3, and all of the points included inside the circle as well, right, inclusive of the boundary. All right, so that's how we would sketch this region. Now let's jump into another example. So for a second example, we are given the set, right, r theta such that 1 less than or equal to r less than or equal to 1 minus 2 cosine theta. And theta runs between pi over 2 and 3 pi over 2. Okay. All right. So it'll look like this. Our set. Okay. right. So now the difference here is that these aren't constants, right? Or at least one of them is, right? R is greater than or equal to 1, but less than or equal to 1 minus 2 cosine theta. All right. So, and the angles run between pi over 2 and 3 pi over 2. So I want to get an idea of what this looks like, right? Before I put it in my polar graph, I'm going to look at the Cartesian coordinate graph of this, right? The rectangular coordinates, right? So again, even though we are dealing with polar coordinates, one way to graph polar equations is to start with our rectangular coordinate system like we've been used to doing our previous graphs. And the graph of this, so I'll graph 1 minus 2 cosine theta, looks something like this, right? Right, our angles of interest are between pi over 2 and 1, 2, 3 reaches its max value there. All right. And this is pi over 2, and this is 3 pi over 2. Okay. All right. So as we could see here, this is, again, right, even though we use this as our theta and our r axes, this is not a polar graph. This is a rectangular coordinates graph where each coordinate corresponds to a direction in theta and a direction in r. Right? That is not how our polar coordinates work. Right? As we have seen in previous sections, polar coordinates are described by the distance from the pole and then a angle. All right. So I want to draw that, right? That's what I'm actually hoping for, right? So just keep in mind this is not polar coordinates. These are rectangular coordinates. But they do tell me a lot of information here, right? Between pi over 2 and 3 pi over 2, we see that the minimum value of r is 1, right? If these are the value of r. So let's actually get to drawing our polar coordinate system. All right, so measured from the positive x-axis, pi over 2 is here. So we're going to start here. And at pi over 2, the value of r is 1. All right, so if we call this 1, we start there. And we notice, well, what happens to r, right? And this point here is pi. So it increases to its max value of 3 at pi. So if this is 1, 2, 3. So I know that it increases to its max value of 3. Well, then what happens after that, right? So this is between pi over 2 and pi. We have positive values of r. As you work from pi to 3 pi over 2, now these values, they're still positive, but they're decreasing till they get back to 1. So as I move down here, call that one, right, to our value of r. Okay, and again, this includes all of the r values in between, so it would include all of these values in there. Okay, and now this is a polar graph, right, where it's all in terms of the values of r and the angle theta that is getting sucked out by. All right, so the next thing we're going to do is we're going to move on to a different type of example. For these next examples, we're going to be given a graph, and we want to use set builder notation. So let me write this down. So for these next examples, we want to use set builder notation to describe the shaded region of the graph. All right, and we'll be using polar coordinates. All right. So for our first example in this type of problem, we have okay, so bear with me here as I draw these graphs. Okay, so we have here are some semicircles. Right, of radius 2 and radius 3, and we're looking to represent this area here. All right, including the boundaries here. All right, now in terms of our Cartesian coordinates, we have two semicircles here. So we have x squared plus y squared equals to 4. X squared plus y squared is equal to 9. All right, okay. All right, and again, these are all for both of these. In this case, y is greater than or equal to 0. So we're just looking at the top halves of these circles. Okay, so in terms of set builder notation, all right, again, right, that set builder is we're going to have curly braces to signify our set. All right, it's in polar coordinates, so r theta, such that, and in here we need the values that describe r, right? So as we look at this, we see, all right, the values of r, regardless of where we're at here, is they range from 2 to 3, right? Here, 2 to 3, right? The distance from the pole, right? So the circles, right, the equations of those circles in polar coordinates are super simple, right? If this is the radius squared, it's just r equals the radius. In this case, 2 and 3. All right, so it's always constant, right? In terms of the distance from the pole, it doesn't change. So the r part would be this. Right? Any values of r that are between 2 and 3. Now, in terms of theta, right, it doesn't do the full circle, right, the full 2 pi radians. What it does do is that it goes from 0, the half circle, which is pi. So we could say, all right, theta runs from 0 to pi. Okay. All right, and that is it, right? That describes the set, right? This graph that we have here is represented by our set builder notation right there. All right, let's try one more example. So for this one, for number 2, describe the region using set builder notation. That is in the first quadrant. And bounded by y equals to x equals to 2, and x equals to 3, and the x-axis. Okay. All right. So now the first thing is, well, let's kind of draw to see what this graph looks like. Right. The first kind of step in trying to solve a problem like this. So it's in quadrant 1, so it's where x and y are positive. Y equals to x is a straight line going through the origin of slope 1. Right, x equals 2 and x equals 3, those are just vertical lines. And the x-axis, of course, is that right there. All right, so we would like to describe this region right here, right? That is bounded by all of those curves, right? Y equals x, x equals 2 and 3, and the x-axis, right? That's the only region that it could be. All right, now in determining this, right, we're going to use set builder notation, right? This is much different than our circles, right? Because our circles just have a constant value for r. Now we do know that, at least here on the right, that the lower limit here, right, if we want to start here, right, our lower limit is not always 2, right? It's 2 to 3 here. But if I move up here, this distance here is not 2. Right? When we have that nice kind of sweeping out like a circle, it was always 2. But this distance here isn't 2 anymore. Right? And from here to here, this distance is not 3 anymore. Right? In fact, that distance is, again, we're taking a distance from the pole, is much bigger than 3. Well, I shouldn't say much bigger. It's larger than the value 3. Right? Well, how do I know what is trapped between here? Well, let's look at some of our x equals 2, some of our polar coordinate transformations, right? When we transfer from Cartesian to polar, right? I can use the substitution, right? X is r cosine theta. I can divide by cosine. And from our previous work that we've done with trig functions, the reciprocal, 1 over cosine is secant. So r is 2 secant theta. Right? So as it turns out, the distance from here to here, right, depends on what is the value of theta. So this would be r is equal to 2 secant theta. So that would be the lower limit, right? And the upper limit up here, right, that would be r to 3 secant theta, right? Using the same kind of transformation of coordinates here, right? So, not x, r. So we could see here in terms of our set builder notation, which I'll draw down here, we'll have r theta such that r is bounded on the lower end by 2 secant theta, on the higher end by 3 secant of theta. Okay. Now in terms of the angle theta that is swept out is from here, right? And the way we find that is we say, all right, well, what is this line? This line is y is equal to x, right? And dividing by x both sides. And again, using our coordinate system from rectangular to polar, this is tangent. Right? And in quadrant 1, that angle theta is pi over 4. So it sweeps out from 0 all the way up to pi over 4. Right? So we would get that. Right? And that is how we can convert something like this into set builder notation. Now I know that in terms of lines, right, using algebra or our Cartesian coordinates, it's easy to work with lines. Our polar coordinates, since it's nice with curves, it's a little bit tricky working with these straight lines, but not impossible to do, right? Just keep in mind what you're dealing with when dealing with straight lines and polar coordinates. All right, thank you.